Hello, welcome to our classes. I am Dr. K.K. Misra. This is the part 4th of the series of queuing theory theoretical aspects, wherein I have been uploading video tutorials on the previous part 1, part 2, part 3, the theoretical aspects, methods, and procedure of queuing theory. Here in this video tutorial, the topics which I will be covering, that is Poisson-exponential, single server model, finite population, and multiple server model, infinite population. Let us take up the first one. This queuing model is based on similar assumptions as the earlier discussed model uploaded in the previous video tutorial, except that the input population is finite. Let there be a total of m customers in the system. A customer is either in the system, that is consisting of a queue and a single service station, or outside the system and in a sense arriving. In particular, when a customer is in the arriving condition, then the times it takes him to arrive is a random variable having an exponential distribution with mean mu with mean is equal to 1 upon lambda. As a result, when there is n customers in the system, then there are m minus n customers in the arriving state, and therefore the total average rate of arrivals in the system is lambda into m minus n. It may be observed that the system is here self-regulating. The operating characteristics of such system are given here, with m as number of customers in the source population, 1 upon lambda as the average interval arrival time between successive arrivals, and mu as the service rate. We have probability that the system shall be idle, P0 is equal to summation I is equal to 0 to m factorial m upon factorial m minus I and lambda upon multiplied by lambda upon mu to the power minus 1. Probability that there shall be n customers in the system, here Pn is equal to 0 to P0, that is lambda upon mu to the power n into factorial m upon m minus 1 for all 0 is less than m and greater than or equal to m. Now see expected length of q, that is LQ. Here m, this is equal to m minus lambda plus mu upon lambda multiplied by 1 minus P0. Then we have expected number of customers in the system, that is D. Here Ls is equal to LQ plus 1 minus P0 or m minus mu upon lambda by putting the value 1 minus of LQ from the previous one. So we can have this m minus mu upon lambda multiplied by 1 minus P0. E, expected waiting time of a customer in the queue, that is WQ is equal to LQ upon mu into 1 minus P0 or 1 upon mu within bracket m upon 1 minus mu0 P0 minus lambda plus mu upon lambda. Expected time a customer spends in the system, that is WS is equal to WQ plus 1 upon mu, and that's how we can calculate it. Now, Poisson-exponential multiple server model, infinite population. Each of the previous two models were discussed on the assumption that there is only one service facility in the system. Now in this model, there are multiple service facilities giving identical service, and this model depends on the following assumptions. Here the assumptions are: the arrival of customers follow Poisson probability law, the average arrival rate being lambda. The service time has an exponential distribution. There are k service stations, each of which provides identical service. A single waiting line is formed. The input population is infinite. The service is on a first come first served basis. The arrival rate is smaller than the combined service rate of all k service facilities. Now, operating characteristics. Lambda here, average rate of arrivals, mu, mean service rate of each of the servers, k, number of servers, k mu, mean combined service rate of all the servers, and rho, lambda upon k mu, utilization factor of the entire. The operating characteristics here are given. Probability that the system will be idle. Here it is P0 within bracket summation I0 I is equal to 0 to k minus 1 lambda upon mu to the power I upon factorial I plus lambda upon mu to the power k upon factorial q1 minus rho whole to the power minus 1. B. Probability that there shall be n customers in the system, that is Pn is equal to P0 lambda upon mu to the power n upon factorial n when n is less than or equal to k, and Pn is equal to P0 lambda upon mu to the power n upon factorial k factorial into k to the power n minus k when n is greater than k. The expected number of customers in the waiting line, that is LQ. So here lambda upon mu to the power k into rho upon factorial k 1 minus rho to whole square multiplied by the whole expression multiplied by P0. The expected number of customers in the system, that is LS, is equal to LQ plus lambda upon mu. The expected waiting time in the queue, that is WQ LQ upon lambda, and the expected time a customer spends in the system, that is WS, is equal to WQ plus 1 upon mu. So this was the complete theoretical aspect of queuing theory. Now in the successive video tutorials we would be taking up practical problems. For any queries you can write to ourclasses@gmail.com. For other video tutorials available on the topic and other chapters of operations research, you can follow our classes. Thank you. Please like, share and subscribe. Thank you very much. Have a nice time.